Hello, everyone. All right, so let's get into the actual course of our grade 12 university level physics. So this is Unit 1, Lesson 1, and we're going to be talking about, well, really, we're going to focus on motion on an inclined plane, but really we're going to introduce um, a pretty big idea for this unit. This whole unit is basically dynamics. We're looking at why things move. And we're going to take what we've learned about Newton's laws and kinematics from last year and just extend it to more difficult problems. And even start with looking at something called the non-inertial frames of reference and non-inertial problems, which are interesting. Okay, so the big idea, though, for this whole unit is about frames of reference. Okay, you've probably heard this before. But whenever we look at a problem, the first thing we have to do is establish some sort of a frame of reference of how we are looking at it. Okay, this defines what we call a coordinate system, like an x, y, and a z if it's in 3 dimensions, or just x and y. A Cartesian, typically, coordinate system. You can also use polar coordinates. That's when you use a radial distance and an angle. But in our class, we're never going to look at those. We're just going to look at usually a Cartesian coordinate system. And the point is, we want to pick a frame of reference that makes the problem easiest for us, so that we can solve the problem in the most efficient way possible. Right? There's infinite ways of doing it, but we want to pick a way that has the fewest amount of steps, fewest places for us to make mistakes, really. And we can do this because of the concept of a frame of reference being valid. The laws of Newton's laws being valid in all those frames of reference. So anytime we have a frame of reference that isn't moving or is moving at a constant rate of change, constant rate of speed, we call that inertial. So an inertial frame of reference is a frame of reference that is stationary or is moving with a constant velocity. And what's amazing about Newton's laws is that it doesn't matter what the frame of reference we have. All of Newton's laws are valid in all inertial frames of reference. Once we have an accelerating frame of reference, what we call a non-inertial frame of reference, things get a bit more complicated, and Newton's laws have to be modified slightly. It still works, but we just have to make a few modifications. Right? And this helps us with any sort of problem, because it means that we can pick any frame of reference that just works, that just helps us. Okay? So we're just going to switch over here. We're going to do something different. We're going to try to watch a movie. Okay? This is from YouTube. I'm going to put the link in the description. This is a very old movie. It's from the 60s. I think it's 1960. It's actually from the University of Toronto. It's all about frames of reference, but it's actually really good. Okay, it's black and white. Sound is pretty bad, but it really does a good job of describing how frames of reference are useful. Okay, so let's try this.
We are used to seeing things from a particular point of view, that is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
So who's upside down? Can you tell? Can you tell who's upside down right now? Whose frame of reference are we in? Are we in the frame of reference of the professor on the right or the professor on the left?
You look peculiar. You're upside down.
No, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down.
So we needed gravity, which actually provides a non-inertial frame of reference, to provide us the answer. When we could just see them, we had no idea. Now we can see the one hanging upside down. But previous to that, both frames of reference were valid. It's just when you add something like gravity, which produces a non-inertial frame of reference, we can actually differentiate which frame of reference is correct.
You better come into my frame of reference now.
My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference, just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction.
So we were able to use these axes, in this case it looks like an XYZ axis here, to define our frame of reference. And what's important is that we have an origin, right? We have the intersection of those 3 that defines our reference point. Everything is going to be measured from that origin where those intersect. That's sort of our 0, right? Our 0, 0, 0 if it's X, Y, Z. And that will define where we're sort of looking from. Defines our reference point, our reference frame.
You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not.
And that's a very important point. So if, let's say, quick little thought experiment here. Imagine you are in a completely encased box. This box has no connection via any sort of experiment, via light, via sound, via anything. There's no communication between the inside of the box that you're in and the universe. There is no way, there's no experiment that you can do inside that box that can prove that you are at rest or you are in motion. You are in an inertial frame of reference, and there's nothing that you can do. All the frames of reference are correct, and there's no way that you can prove that you are moving or you are not moving if you have no connection. When he was sitting there with no visible frame of reference, there is no way to tell whether he is moving or whether he's not moving. We have to have some sort of way to look at it. So here we're going to see previously the background is moving, but now what happens?
But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is that the position of any object, such as this ball, can be specified using these 3 reference lines.
Sorry, 1 second. Let's go. Here we go.
This reference line points in the direction which we call up, which is a different direction here than it is on the other side of the earth. And these 2 reference lines specify a plane, which we call horizontal or level. In this film, we're going to look at the motion of objects in this earth frame of reference and in other frames of reference moving in different ways relative to the earth frame. Well, let's look at a motion. This steel ball can be held up by the electromagnet. Now I'm going to open the switch, and you watch the motion of the ball. The ball is accelerated straight down by gravity along a line parallel to this vertical reference line.
As you can see, the electromagnet is mounted on a cart that can move. And I'm going to do exactly the same experiment that Dr. Hume did, but this time while the cart is moving at a constant velocity. The cart is pulled along by a string which is wound around this phonograph turntable, and that pulls it with a constant velocity.
So what's the path going to be for the ball when it's dropped in this situation? It's moving to the right at a constant velocity. What's the path going to be relative to the cart? Or
when the cart
relative to
passes this line,
lab frame,
the ball is released, as you can see. I'm going to start the cart down at the end of the table so that by the time it gets to this point, I can be sure it's moving with a constant velocity. Now, I want you to watch right here so that you will see the ball falling.
So here we're in the lab frame, we're in the stationary frame. What was the path that we saw in the lab frame?
I think you can see that the ball landed in exactly the same position that it did before.
So it's straight
when
in
Dr. Hume
the
did the
cart
experiment
frame.
with the cart fixed. But this time, the ball could not have fallen straight down. Let me show you why. The ball was released at that point. If it had fallen straight down, because the cart moves on in the time that it takes to fall, it would have landed back here somewhere. But it didn't. Now I'm going to do the experiment again. This time, I'm going to let you watch the motion through a slow motion camera.
So what's the path going to be from the viewpoint of the slow motion camera? What are we going to see? What kind of path, what kind of shape is it? Is it going to be a line? Is it going to be a parabola? Is it going to be sinusoidal? What's the shape of, what's the relationship going to be? Think about it in terms of components of vectors. There's a vector pulling down with gravity, accelerating at a constant acceleration, and it's traveling to the right with a constant velocity. So if I put those things together, what kind of shape am I going to get?
Which is fixed. Here, as the cart moves by, the ball will fall, and you can watch in the slow motion camera.
What
I'll
shape
show
was
you
that?
this again. This time there'll be a line on the film so that you can see the path.
If you said parabola, you were correct. Right? The y component of the of this position here, this y position, is increasing as a square, and it's traveling to the right as linearly. So you put that together, we end up with a parabola.
I think that you can see that the path of the ball is a parabola. But all of this has been in a frame of reference fixed to the Earth. How would this motion look in a frame of reference which was moving along with the cart? Frame of reference like that. Well, so that you can see what it looks like, I'm going to fix this slow motion camera so that it moves with the cart. Like this. I'm going to do the experiment again. And incidentally, I'll start it, and then I'm going to stand here so that when the ball falls, you will have something which is fixed as a reference point.
So what are we going to see now? It was a parabola before, but now when we're traveling with it, it goes straight down. Both of those viewpoints are correct.
In the moving frame of reference, I think you could see that the path of the ball is a vertical straight line. It looks exactly the same as it did before when Dr. Hume did the experiment with the cart fixed. If we were moving along in this frame of reference and we couldn't see the surroundings, then we wouldn't be able to tell by this experiment that we were moving at a constant velocity. As a matter of fact, we wouldn't be able to tell by any experiment that we were
As I
moving
just said.
at a
Yeah.
constant velocity.
There's
I'm
no
going to do the
experiment we can
experiment
do.
once more, and this time I'm not going to stand here behind the ball as it falls so that you won't have any fixed reference frame.
There you go. Okay. All right. So let's stop this
As
for
far
now.
as you're concerned that time,
There's much more. It's about a half-hour video. We will be looking at it again, I think, in lesson 5 of this unit, but we'll leave that for now. Okay. So the point there again, all frames of reference are correct. All frames of reference, Newton's laws are valid. Okay. So let's look at an example here. So let's say we have Mr. Stone. He's in a cart. Okay, and he's going down an inclined plane, and the angle is 20 degrees. The ramp is 20. The ramp is 20 meters long. How fast is he going when he hits the curb at the bottom? So really, how fast will he be travel? Will he be thrown out of the cart because of Newton's laws? Let's assume he's 100 kilograms. That's a bit much. Oh well. And the coefficient of friction is 0.01000. No units on that. So this is what we're given. So the picture looks a bit complicated, but let's simplify it. This is how it's physics. We always do that. We take our picture and we make it simple. We have our inclined plane. We have an angle of 20 degrees. We said that's our theta there. And we have our mass, m, which we're going to, that's me. And we're going to use just a box to represent it. So what we're going to do now is decide what our frame of reference is going to be. And you might think, okay, well, we'll just go X and Y, up, down, left, right. But really, that's not the best way of doing it, because the motion is going to be traveling parallel to the cart, right? It's going to go up and down. It's not going to be going, up, down, left, right. It's going to be going with the ramp, right? The ramp is going to define the way that it moves. So let's use the ramp as our frame of reference. We're going to say that our coordinate axis is parallel to the ramp. So parallel to the ramp here, or perpendicular to the ramp. And then we're going to decide that going down the ramp is in the positive direction. Up off the ramp is positive, and into the ramp is negative. Okay, so this is our frame of reference, FOR. Okay, that defines how we're going to measure things. So let's now think about some dynamics. So first thing we can think about is the fact that gravity is going to be acting on this object. Gravity is the main source of its motion, right? Gravity is going to be pulling it down, but gravity is going to be pulling it towards the center of the Earth, not down the ramp. So we're going to need to take our gravity vector, which is not in one of the directions that we picked as our frame of reference, and break it up into components. So we're going to take it and we're going to break it up into two vectors. So instead of going straight down, we're going to go one vector perpendicular to the ramp, and another vector parallel to the ramp. Okay, and so really the motion is going to be caused by this parallel vector. The one that's perpendicular is just pushing on the ramp, and if that was the only vector that was there, the mass would just somehow bury itself into the table or into the ramp. But because there's a ramp there has to be a normal force that opposes it. Remember normal force? This is the force that opposes it's normal. It's at right angles to the surface. It stops the motion from happening in this case. So as I push down onto the ramp itself pushes back against it because of the material in there. The atoms in the ramp are going to electrostatically repel the atoms in the mass. They're going to balance out. So these two vectors, Fn and Fg perpendicular, will cancel out. So it will not levitate off the thing and it won't go into it. Just quickly, I didn't actually say this, but this angle here, theta, is the same as the angle here, theta, and that's due to similar triangles. This bigger triangle is similar to this triangle. So we can say, because of the law of similar triangles, the angles of a similar triangle are all the same. This is right angle here. So that theta is the same as this theta, which means that we can do trigonometry here. So we could say that this FG parallel is going to be what? FG, what's that? That's opposite, so that's sine theta. And this one will be FG cosine of theta, right? Because this is adjacent and this is opposite. And we also said that there's going to be a frictional force which will oppose the motion, right? We said that it's, right, if I just let go, the velocity is going to be going down the ramp. So friction will oppose that. So the direction of the friction vector will be parallel to the ramp, but in the opposite direction to velocity. All right, so here's a nice little free body diagram which shows all the forces that are acting on this thing. Right, and you can see it has a balanced force perpendicular to the ramp. It's not hovering off the ramp, it's not going into the ramp. Those two vectors, this one and this one here, they cancel out. But the parallel component is actually going to pull the mass down while being opposed by the frictional force. So how do we now figure out how fast we're traveling? Basically, we have to figure out the acceleration. So all these problems, pretty much everything we're going to do in this unit, we're always going to start with Newton's second law. F equals ma, written as a vector equation right now. Okay, we're going to change that, but right now we're just going to leave this as a vector equation. So the question becomes, what is that force? Remember that F is the net force acting on the thing. So net force is proportional to the mass and the acceleration. The more mass, the more the harder it is to push it. The more you accelerate it, the faster it goes. Right? So we know, if I just flip this around, instead of F equals ma, let's go ma equals F. The F, the unbalanced force, the force that actually matters, that actually is going to cause the motion to happen, right? The acceleration is going to go down the ramp, right? It's going to pull down the ramp. So the only forces that matter are going to be the blue vectors, because they're the ones that are in that direction. So that's going to be, now I've written this as a vector equation, so I can use plus in this case. When I add vectors, I just use plus. The directionality of the vector is in the vector itself. I'm just adding the vectors together, so I'm using a plus sign. This does get a little bit complicated at some points here, so just be kind of careful with what you're doing here. So when you're adding the vectors, we're always going to use plus. I'm going to switch now from a vector equation to just the components. Notice all the vector signs have gone away in this third line. I'm only now looking, this is now a component equation that's only in the, not perpendicular, that's only in the parallel direction. So the mass times the acceleration in the parallel direction is equal to mass times gravity times sine theta, right? We said that this FG down here is going to be, let's go back here. Well, maybe I'll just do it here. We know FG parallel is going to be FG sine theta, and Fg itself, the force of gravity acting on this thing, is going to be mass times acceleration due to gravity, which is Fg sine theta. Similarly, the force of friction will be, remember that force of friction is equal to mu Fn, the coefficient of friction times the normal force. And we know that the normal force is in the opposite direction to the perpendicular force here. And that perpendicular force, so this is going to be mu, Fn is going to be Fg perpendicular, and then Fg perpendicular is then mg cos theta, right? Because it's the adjacent side. Right, if you're stuck on these sines and cosines, maybe I'll just scribble somewhere here. Remember that sine of theta is equal to opposite over adjacent. So opposite side is going to be FG parallel, and then the hypotenuse, sorry, its sine is opposite over hypotenuse. So that's just going to be FG. So then I can multiply both sides by FG. So then FG parallel is just going to be force of gravity times sine theta. Okay, that's where that comes from. And you can do the same thing for cosine. So really it just becomes the same thing. So the force of friction is the same piece except for the cos. And then we multiply by mu, that unitless coefficient that tells us how much we're actually slowing it down by. Remember, mu is the sort of the way it tells us how much a surface stops motion. So if it's glass doesn't stop motion much. So its coefficient of friction is very small, 0.00 something or other. If there was no wheels on this cart and it was just a box scraping down the side of a hill, that would have a pretty large coefficient of friction, something in the order of like 1 or 2. All right, so that's where we came up with this formula here. So this is the component. This mg sine theta is our force of gravity parallel, and our force of friction is our normal force, mg cos theta, multiplied by mu. All right, so this equation really tells us everything we need, because now we can rearrange it. We can divide by m. Oh, that's great. The mass doesn't matter. It doesn't matter how heavy Mr. Stone is. His acceleration won't change. Okay, the mass cancels. Mass is everywhere in there, so I can divide the whole thing by m. So we have a equals g sine theta. And if there was no friction, that would be it. My acceleration would just be g sine theta. But my friction is going to slow us down by amount, which is going to be g cos theta multiplied by mu. Then I can plug in all my numbers, right? G is 9.81 meters per second squared, sine 20, cos 20. I'm going to put all my numbers in here, and I'm going to come up with a number of 3.26 meters per second squared. So it's about a third of gravity. I'm accelerating at about a third of gravity. All right? Now, unfortunately, that wasn't what the question asked. The question said, hey, what's our velocity going to be? So we're going to have to do one more step here. Because we have to find the velocity, we can go to our kinematic equations. These are in our formula sheets. We can now, we know that I'm starting at rest, so V1 is 0. 0 squared is gone. And then I can plug in my answer, which was 3.26, in for A, square root both sides, and I come up with 11.4 meters a second, which is almost 38 kilometers an hour or something like that. Wow. Ouch. That's going to hurt. Okay. So I'm going to round this because of significant figures, because the 20 has 2 sig digs. I'm going to have to round that to 11 meters a second. And finally finish the question, therefore statement, right? Therefore, Mr. Stone is traveling at 11 meters per second at the end of the ramp. Okay. So we can go back here. We can go back again. Remember what we did. How do we do this? Let's just sum up again. So what did we do? We started with a frame of reference. Then we drew ourselves our free body diagram. Then we wrote F equals ma. We wrote out what the vectors we care about, the ones that are actually causing the motion. Then we wrote them instead as a component in the direction of motion. And then I solved for A, plugged in my numbers, I got a value, and then I used that in another kinematic equation to come up with my final answer, remembering to round to the appropriate number of significant digits. Okay? Awesome. All right, so let's do another one. Same idea, same thing, but this time I'm being pushed by my evil twin. Okay, and when I hit the ramp, instead of me traveling at 11 meters a second, I'm traveling at 18 meters a second, which would be what? A lot. Close to, what would that be, like 65 kilometers an hour? Ouch. What have I done? All right, anyways. So same idea. Let's make ourselves our diagram. I draw a picture. Define our frame of reference, again, with the plus going down and the plus going up. We draw our vectors in the same way. And the only difference now is that I have an applied force. Let's call this FA, pushing down the ramp as well. Okay, so the new part of this question is I just have this FA. All right, so since we know the velocity in this case, and it's asking for, what is it asking for? Let's go back here. What was the applied force? So we're going to go backwards in this case. So we're going to take our problem and start with our kinematics. We know the initial velocity, so let's find the acceleration. So I'm going to solve my kinematic equation. I'm going to, well, again, there's no initial velocity. It says it starts from rest. Divide both sides by 2 delta d and substitute in my numbers, and I end up with 8.1 meters a second squared. So that's my acceleration. I'm accelerating very fast. Okay, 8.1 meters, that's almost falling. And now once I have my number, I can then go to my F equals ma problem here. So again, we always start these problems with F equals ma, and then I rewrite it as what is my net force. So in this case, my net force is going to be whatever the blue vectors are. Again, we have our force of gravity pulling us down. We have our force of friction opposing that. Again, I put a plus, but that will be really a negative. And the force of the applied force is again pulling down. So when I replace my values in the same way, I have again force of gravity, that's going to be the opposite side. So that's going to be mg sine theta. The perpendicular part will be fg cos theta, but then I'm going to multiply by mu again to get my friction. Being very careful that I'm subtracting here. Remember that I'm subtracting because it's opposing, it's in the opposite direction. Again, this is a component equation. This is vectors up here. This is a vector. This is in components. And the new piece was my force applied, which I'm going to add here. And notice I'm adding it because it's in the same direction. Right? In my frame of reference, the negative direction was to the left, the positive direction was to the right. So these two vectors are going to be positive, and the force of friction is going to be negative. So my equation, positive, negative, positive. Okay? So then I can do the same thing. I'm solving now for FA, right? I'm going to bring everything over. I brought the mg sine theta over, that became negative. I brought the mu mg cos theta over, that became positive. I can factor out mg. I can factor mg out. Mg is in this term, mg is here. And there's no mg here, so when I take mg out of ma, I'm going to be left with a divided by g. Okay, see where that happens? mg times a over g, the g's will cancel, and I'll be left with ma. mg, if I multiply this into a over g, I'll get mg a over g, and then the g's will cancel. Or maybe I'll write that down. mg a all over g, so the g's will cancel, enough with ma. So when I factored out mg, I'm going to be left with a over g. And then subtract sine theta plus mu cos theta. Notice this term, this bracket here. What are the units going to be for that bracket? Units for this thing are going to be nothing, right? Because I have meters per second squared divided by meters per second squared. They'll cancel. And then sine and cosine, they're all unitless expressions. So really, this term is just telling me, like, mg is my force of gravity pulling down. And then I'm going to be making that bigger or smaller by this factor, this ag minus sine theta plus mu cos theta. So at this point, I have all these things. I have mass, I have g, I have a, right? I calculated that before. And I have my thetas and my mu's. So I can replace everything in my expression. 100 kilograms. This point, the mass does matter, right? Because the more I push, the heavier Mr. Stone is, the less the force will matter, right? Because they're inversely proportional. The heavier something is, the less forces act on it. That's called inertia. So I plug in all my numbers, and my applied force is 483 newtons, or 2 sig figs at 480 newtons. And therefore, my head's in the way. No, it's not. We have a therefore statement. The cart is being pushed with 480 newtons of force. Okay, so there's another one. Same idea. Same. All these inclined plane problems are the same. Draw a picture. Draw a free body diagram. Sorry, I missed a step. Make a frame of reference with your pluses and minuses on there. Then draw your free body diagram according to that frame of reference, and then you can go from there. Typically, we're always going to have these problems starting with F equals ma. We had to do a little bit of work in this case before, right? We had to find a. But typically always start with F equals ma. Pretty much everything in this whole entire unit is going to start with that beautiful Newton's laws, Newton's expression. You ever wonder why am I here? Why am I here in Cambridge? This is Cambridge University. This is the quadrangle of Cambridge. And one of these windows here is where Newton actually lived when he was going to school here when he was 19 years old. All right, so let's do one more problem. Say we're going to do a little bit opposite now. I'm going to be pushed up the hill now. And I'm going to be pushed and pushed and pushed. I'm going to get to 5 meters a second, and then whoever's pushing me is going to stop. Okay, so I have initial speed of 5 meters a second on this same 20-degree hill. If I now have a bigger coefficient, because of all the times I've crashed into the bottom here, the wheels don't work so well. The coefficient's gotten larger. Now it's 0.1. How far up the hill am I going to roll until I stop? What's my rolling distance? I'm going to be push, 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 and then let go. How far do I keep going if I'm traveling 5 meters a second? So how are we going to do this one? So again, same idea. Draw your picture. Draw your frame of reference. And now, because I had velocity in the up direction, I'm going to do something a little bit different. In this case now, the plus is going to be the up the hill direction. The plus is still going to be, on the perpendicular direction, sorry. The plus is still up from the ramp and the negative is still down from the ramp. But because my velocity is up the ramp, I'm going to define the plus direction to be up the ramp as well. And again, we have force of gravity. We can break that up into components. And now, be very careful. Because I'm traveling up the hill, friction will be pulling down the hill because it's opposing the motion. Friction always opposes the motion. So notice now that the force of friction and the force of gravity are in the same direction. Okay. Previously, when we were going down the hill, friction was slowing us down as we were trying to accelerate down the hill. Now we're trying to decelerate up the hill, and it's slowing us down even more. So again, F equals ma. Write out our forces. In this case, the only two forces are gravity and friction. And in this case, though, we're going to put negatives everywhere, right? Because I decided that the up direction is going to be positive, up the ramp is going to be positive, gravity is pulling us in the opposite direction, so it's going to be negative mg sine theta. Friction is pulling us in the opposite direction, so it's going to be negative mu mg cos theta. And then again, I can cross out the masses because mass doesn't matter in this case. I can factor it out, plug in all my numbers, and I have an acceleration down the ramp. So I'm decelerating. I was traveling 5 meters a second, and I'm slowing down at negative 4.28 meters a second squared. All right. So again, I can do the same thing with my kinematic equation here. I know that my final velocity now will be 0. Sorry. When I get to the top of I'm being pushed, I'm going. I'm going to stop. When I stop, my final velocity will be 0. So I can rearrange this now for delta D is what I'm looking for, right? The V1 goes over, it becomes negative, divide both sides by 2a. Notice now, when that negative is not inside the bracket. So it's negative 5 squared. So it's going to be negative 25 meters squared per second squared on top, divided by 2 times my acceleration that I calculated. So it's about 3 meters, 2.9 meters, rounding to 2 significant digits. Remember, significant digits. If you get stuck on that idea, go back to the videos there. And if you're still stuck, just send me a message. Okay? So therefore, Mr. Stone travels up the ramp about 3 meters. All right. So again, all these problems are very similar. Draw a picture, draw your vectors, calculate your final answer. Okay. You're typically starting with F equals ma. Draw your vectors, break it up into the components that you need. Make sure you find the components that are the ones that are actually causing the motion, put them into your F equals ma formula, rearrange everything, and we get our final answer. All right. So there's 3 examples. I'd like you to do some homework here. So again, the way this course is set up is it's always going to be the same idea. We're going to have a lesson like this. Apologize for this one being long, but there's quite a bit here. I watched a movie, so there's always going to be some practice problems afterwards, and all the practice problems will have solutions posted on the Weebly. In this case, there's 2 problem sets. This is one of them. There's 3. These are really small. Problem set 2 is a little bit more complicated, but again, I'll post all the answers. If you have any questions, just ask. Okay, I will not ask you to hand those questions in. Now, that's because I physically can't mark all that, and really, this is a grade 11 grade 11 physics class, which is basically math, and math is it's all about practice. So if you want to do well in the class, you have to do the practice problems. All right, so I'll leave you guys now to work on those problems, and I hope everybody's doing all right. If you have any questions, just send me a message on Teams, and best of luck. Take care, guys.